Hello everyone, Risk will Thrive and Survive. We come back to an oldie but a goodie, the Arctic Sun. And I'm going to briefly show you the argument both ways, those that argue the flat earth model, more specifically the geocentric model versus the heliocentric model. Let me say first that this is not a flat earth proof but a geocentric proof. But once you realize that we are the center, even all the other stuff falls apart, like the ball and things like that. So this is an ultimate proof. I would debate Neil Tyson deGrasse, anybody with this. This is something they cannot reverse engineer or hide any longer. I'd like to give full credit to Dave in the UK for this. His brilliance in noticing these kinds of things, these kinds of perspective things, is what brought this to light. And it wasn't until he showed me a model of scale that it finally really sank into my brain. I fell asleep, woke up, and I just knew immediately how to show this to you all so that you could see it. This is the ultimate busting of the heliocentric model. If anyone can disprove this, I will take this video down. Otherwise, this is the ultimate proof, and let's get into it. What is causing this sun to rise and fall? Well, let me give you the argument from the standard science model, because that's the one we're going to be disproving. The argument is that as the sun gets its lowest point in the Arctic, you are actually closest, or farthest away I should say, from the sun. And as it comes up to high noon, you are at its closest point. The reason why it's not equal is because you are not in a location on the earth that is right along the circle that would be necessary to make it equal in the sky. And I'm going to show you that right now. We start with a model that science gives us for the earth. The light source is to the right, the sun, and we are tilting the earth because it is supposedly tilted 23.4 degrees on its axis. That reveals this final result right here, and what you're seeing now would be the representation for the summer solstice, where the northernmost part of the globe would be in 24 hours of light, as you see here. So we're going to pick a point on the earth that we can see here, and then we are going to rotate it and show you what the model says we should see and what we saw in that video. This is the explanation for the rising and falling of the sun. It is important now to do a comparison between the flat earth model and the heliocentric model presented to us by science. We will show the contrast here, as this is going to be extremely important in understanding this proof that this model absolutely cannot be possible. Starting with the flat earth model, the flat earth believers, or the geocentric believers, is that the person who is filming the sun is at position X. On the globe model, that person would be represented here at position X. This is the lowest point on the horizon that we find the sun in the video. Thus, this would be the equivalent of sunrise lower on the globe, or further away from the north point, which is the center on the flat earth model, at least the traditional flat earth model. In any case, we find that the sun on the flat earth model would be the farthest distance away. Because the sun is the farthest distance away, flat earth or geocentric model states that the sun would appear to move towards the horizon. And as it does on a larger circle, as you get farther south on the flat earth model, it would eventually disappear at the horizon or vanishing point. The reason why the sun is very low in the sky on the globe model is that because from this position here, the observer is looking down at the sun. The sun being 93 million miles away in this model, could not have the sun rise and get lower because of the distance. It has to be because of the angle, the 23.4 degree angle tilt. On the flat Earth model, the rising and falling of the sun has to directly do with the distance the sun is away from the observer. For example, when the sun moves to this position, this would be high noon, since the entire distance or diameter here is only so many thousand miles versus 93 million miles from this point to the sun. Now let's observe as the sun rises towards its highest point in the day, what would happen on both models. Here we see as the sun rises, on the flat Earth model, the sun would be rotating this direction, and the Earth itself would be rotating the observer down this direction on that model. We now reach the apex in both models. Now let me demonstrate what has happened. At the apex or high point, the sun on the flat Earth model would also move counterclockwise in its own circuit until it reaches the high noon or closest position. Again, the reason that the sun would be the highest in the sky is because the sun moved closer to the observer, thus invoking perception and how that works with how things in the sky move towards and away from the horizon depending on the distance. Although I cannot physically rotate the Earth here, let's imagine that this spot is rotating with the Earth. And when the observer rotating with the Earth reached this position here, he would then be at the noon position. Now why would the sun rise in the sky for this person? Because this person started out back here, and although I have this all the way on the right here to show where the sun is, and of course I can't show the scale, but the sun is only a 4-degree arc in the sky. To look at the center of the sun, the observer here would see it down near the horizon here, but as he physically himself was turned on the Earth, he would be lowered, thus rising his viewpoint of where the center of the sun is. So he would then see the point like this higher in the sky. This explains perfectly the geocentric position. Now I want to state something that should be very obvious, but I just want to make sure we make the right point. When the sun then goes from its highest position back down to the bottom, it would be the person in this location here rotating back up to the higher position again, which would lower the position of the sun in the sky. And I'm going to show this perspective type of deal separately here in just a second. I want to point out, however, that in the southern hemisphere the same thing is happening. As this part of West Africa turns, what is going on? Because it's tilted at 23.5 degrees on the axis here. As the Earth rotates, what's happening? Africa is actually heading down in relation to the sun. So as it heads towards noon, when it gets here, the sun would be in the highest position. When Africa is back over here, right at the border between light and darkness, is when it appears that the sun is at its lowest point. Why? Because Africa is at its highest point on the Earth. It drops down in its perspective. It doesn't just work in the Arctic, it works everywhere else, in the north and in the south. The only difference is in the Arctic Circle, because of the tilt of the Earth on the geocentric model, on the heliocentric model, you would have daylight the whole time because of this tilt. Okay, here we are looking at a fixed object in space, the red box on the left. We are the observer, the yellow pin in the center. Now, if there is no reference point behind the fixed object in space, if we begin ourselves to be moved lower, that object in space will appear to rise from our vantage point. It doesn't matter how close or how far that object is, this is what we will get from moving lower and lower and lower, and vice versa. If we were to move higher, the object that's distant in space we were looking at would appear to drop from our vantage point. This is exactly what we were looking at on the heliocentric model. Because the Earth is tilted at 23.5 degrees, we get this rising and falling effect not the distance to the sun as the flat Earth geocentric model would pretend to have. So let's find out if this model holds water.
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer.
Okay, let's interrupt this video at this point because this is a very important point right here. We're going to be comparing the summer solstice and the winter solstice. And when I say summer or winter solstice, these are always in relation to the northern hemisphere unless I state otherwise. Again, this is the representation, June 21st, of summer in the northern hemisphere. Here is the sun over here, and I want to say before I get into this, this has absolutely nothing to do with the argument, for those who know about this, of the sidereal day or the 24-hour day or high noon rotating every 6 months to the other side. It has nothing to do with that argument whatsoever. That is not what I am speaking to. However, this argument will make that argument totally non-material. It does not matter, that argument. So, continuing. What is going on here is the Earth is rotating in this direction, just like we showed in the earlier animation, left to right. Correct? Since it is rotating in that direction, and you can see up here the Arctic Circle, as I showed, is all in daylight, 24 hours. So, if the Earth is moving in this direction, at first, sunrise would be right here for someone in the Arctic Circle, and the sun would be what? Low on the horizon. See, they see the sun roughly where it is at 90 degrees, the center point. The sun would be low on the horizon, just rising to them. As the day goes on and the Earth rotates, the sun would be rising to their perspective because of the tilt of the Earth, rotating them down. If you drop yourself in a point of space, okay, imagine this southern pole here being a point of space right here. This point right here is higher in relation to this point of space than this point is here. You have dropped lower to that point of space. Actually, the easier way to see it is the northern part. The northern part right here, okay, and the sun. You are higher to the sun than at this point, correct? So you are dropping down. As you drop down, the sun rises. This is exactly what we note. This works perfect on the globe model. Would you agree? Same thing, someone on the equator in Africa, maybe we showed that. This is actually South America here where I stopped it. This would be sunrise to them right here. The sun would be lowest on the horizon, although it would be due east to them, wouldn't it? We're not talking about north-south here. We're just talking about how high it is in the sky. As the day goes on, why does the sun rise? Why does it not just stay right there in the middle? It's because you are actually dropping because of the tilt of the Earth, which makes the sun rise. This is perfect. This describes the heliocentric model perfectly. No one will argue with this. Likewise, someone in Australia down here, New Zealand. Okay, here's Australia here. You're at high noon in Australia. As you rotate on the other side, imagine if you rotate to the other side. You're going up then and the sun would drop as you head towards sunset, correct? As Australia comes out of dark here and comes into sunlight, it will drop, correct? As it drops, okay, right here, you're seeing the sun right on the horizon because you're farther up. You're looking to the sun. As you drop down, you have to look higher in the sky to see the sun. The sun appears to rise, even though the sun isn't moving in its position at all. Correct? This is how we explain this model. Let's continue on. If you do not get this part, please go back to the beginning of this explanation. This is extremely important.
The northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. Winter solstice. On the 21st and 22nd of December, the overhead sun is over the Tropic of Capricorn. It receives the largest amount of solar radiation. On this day, the northern hemisphere is in the winter solstice, while the southern hemisphere is in the summer solstice.
Okay, here we come to the winter solstice. Unfortunately, they're not showing this from the other side of the earth, so it's going to make it a little bit difficult. You're going to have to use your imagination a little bit. But let's look what is going on now. And I will show you a picture here in a minute. In fact, let me show you that picture right now. Okay, I'm going to take the bottom part of this off in a minute, but I want to read this to you just so you know I am explaining the correct heliocentric model. Why don't our clocks have to change by a full 12 hours between summer and winter solstice to account for the fact that we are on the opposite side of the sun? Again, this is talking about the sidereal day moving and the supposed flipping of noon from one side to the other of the sun. I am not talking about that argument whatsoever. Forget about that. What I do want you to note here is that they agree, and we all agree, okay, the fact that we are on the opposite side of the sun, okay? That's what I want you to note, because what I'm going to do here is I'm going to take that part off because it doesn't matter to what we are talking about. So let's take a look at this. We started with the summer solstice, where the northern hemisphere was tilted towards the sun. And as the year goes on, 180 some days later, about 182, 183, we're on the other side of the sun, correct? That's correct. The sun doesn't move in relation to the earth. We move around the sun according to this model. Now, as we saw, we rotate counterclockwise, and as you can see, rotating counterclockwise. Notice all 4 seasons we are pointed towards the north, Polaris star. If I could put that on here, you would see that this doesn't change, okay? Now, we rotate counterclockwise all the time. So we're going from here over to here. So if we're on this position of the earth, and it's not, I wish it was tilted more to show you, but you understand. You start from the high point, which would be sunrise, as soon as you get into light, and as you're going down. You're tilted towards the sun, right? You're tilted down, and as you tilt down, or as you move down in your point of reference in space, something that has no reference point will appear to rise in space. This is why the sun rises. I hope people understand that. If you don't have that, you need to talk to somebody. The same thing would work with the equator. It's tilted down. Anybody on the equator, as soon as they see sunrise, it would be low in the sky. And why does it rise? It appears to rise because you're dropping 23.5 degrees. When you get to 12 noon, you're at your lowest point. From that point, you'd be going around the other side of the earth, heading back up again, correct? And as you're heading up, the sun would appear to drop. This is what gives the appearance of sunset, according to this model. So we go along, and then the winter solstice comes, and then we're going around counterclockwise still. And now again, we go into darkness here, okay? We're on the back side. It's midnight. We come around. It's about 3 in the morning back here, and then we come into the sun on the other side. You can't see it, but here is the problem. This is what eliminates this model from being valid. You know, guys, they reverse engineered almost everything perfectly. Almost everything. They missed this. And Dave in the UK and Wales picked this up. And I did a film of this showing that if you put a camera on a globe and have it fixated at a distant light, and I used a very small laser beam at the end of a very long hallway, that if you turn it, tilt it away, the light would appear to be in the form of a smiley face. In other words, it would start at the high point, drop as you moved, turn towards it, and then rise again as you turned away. I put an iPhone, taped it to a globe, and spun it. The problem was I was shaky with it. I don't have anything to hold it at 23.5 degrees, and I have something on it that makes it so it doesn't want to go all the way around. But you're going to see what the problem is right now. Okay, so now we're back to the video model, and this is tilted better to show us. Now, in the winter, when we're on the other side of the sun, when we come into daylight on the other side, we're rising up. We're rising up. So when we're on the other side, coming around counterclockwise, as soon as we get into this light part on the other side, we are what? We're at our highest point of the day. We should first see the sun in the day, high in the sky. As the day goes on, we are dropping. Okay, let me show it from here. Here's high noon. You're at your highest point, which means you have to look down farther to see the sun. As the day goes on and you're heading towards night, you're dropping down in relation to the sun, which would make the sun rise. You are dropping down in relation to the sun. It would make the sun rise to your perspective. This is the major flaw in the model. There is no getting around this. None. You're still pointed at Polaris. You're definitely on the other side of the sun. If you're not on the other side of the sun, they got some big problems with constellations. And everybody that believes in the heliocentric model knows this. This is the flaw that they did not reverse engineer, because you can't reverse engineer it on a ball that goes around to the other side. They even made up all this BS about the time, about we actually turn a little bit more than 1 degree per day because of the path of our orbit, and that makes it so we're on the other side. That's the Sidral argument. And, you know, they reverse engineered all of that. I'm not going to get into that anymore. But they can't reverse engineer what you would see from this. You go from noon at your highest point on the Earth, Southern Hemisphere, okay? Australia, right here, okay? You're right here. You're facing the sun in the middle on the winter solstice, December 22nd. And as the day goes on and you're heading towards dark, you are dropping, just like we did in the Northern Hemisphere in summer, and you did too. Now you're actually going down during the day, because that's the tilt of the Earth requires it. So your highest vantage point during the day makes the sun lowest at noon. Now, to make sure you guys are getting this, because a lot of you right now are having an oh crap moment. Oh crap. And if you're not having an oh crap moment, you're not understanding this. And guys that can do AutoCAD and different things like that, please show this. You can do this. There's somebody, actually Dave is going to show this very clearly. I'm not going to say how he's going to do it, but he's going to show it. And this is 100%, you can't debunk it. Let me show you what I'm talking about here. Okay, here we go, okay? This one right here represents the model we're looking at. When, let's take this part of North Africa here, okay? When it's all going around, it's going through its midnight here when it's opposite, okay? It goes around the back, and when it comes through, it's right here, but it's on the other side, okay? The sun, what would it be? It would be higher in the sky. Then as the day goes on, it would drop. Okay, why? Because you're going up towards noon at here. If you rise in perspective to something in space in the distance, it will appear as if it drops. So at high noon, when we are at the winter solstice, every place on Earth should see the sun lowest in the sky at high noon. Then as the day goes on, okay, it would go here, it would be at its highest point in the sky, and then just, of course, if the Earth is curved, it would just go behind the curve. But it would be at the highest part in the sky when it disappeared, which is impossible. Impossible. People say, well, it would go past the vantage point. but you never see the sun do this. It never dips during the day and rises at night. And guess what? It's that zigzag video that proves this. So, I hope you get this. Let's look at one more thing here. Okay, this one right here is one of the ones that shows it the best. I'm going to say it one more time, and this is one of the best ones. And boy, if you believe in the heliocentric model after this, I got nothing to say except for see a doctor about your cognitive dissonance, because you cannot get out of this. Send this one to Neil Tyson deGrasse. Send this one to Bill Nye, the science guy. The sun is on this side of the earth on the summer solstice. Let's say you're on this meridian right here, coming around. As you come around, what happens? What happens as you come around? As you come around, you're heading downward direction as sunrise happens. When you're facing the sun, it is high noon. You are going down, which means the sun is going up in the sky. Always goes the opposite way of which way you're moving. As noon goes away, now imagine on the other side, you're heading back up again on the other side, heading towards dark. So the sun would be dropping in the sky. So what does the sun do? Okay, the earth do. The earth moves around the sun, right? Nothing has changed, has it? Except when you put the light source on the other side, which the heliocentric model requires. Now the side facing the sun, okay, has the high part going low, okay? This is the way it looks right there. High to low, high to low, high to low, same thing. The difference is where the light source is. When you start coming to the light, you're heading down here. When you're on the other side of the earth here, heading into it, right? You're heading up, so the sun would drop. You get the high noon, you would be at your highest point. Your sun would be at the lowest point in your sky. As you keep going towards dusk, the sun would rise because you're dropping. Yeah, debunk this one. Take care, guys. Enjoy. It's over. It is over. Take care.